Uh, Hello, I'm Jia-Ju from Tsinghua University. I'm very glad to share our paper about bug detection. User-free bugs in device drivers are often dangerous. They can cause system crashes or can be exploited to attack the operating system. Many of these bugs are caused by sequential execution, namely the free and the use are in the same thread. And some of these bugs are caused by concurrent code execution. Namely, the free and the use are in two different threads, so such bugs are more difficult to detect. Here is an example of a concurrency user-free bug in the CW1200 driver. In the driver code, the function CW1200HW scan can be concurrently executed with the function CW1200BSS info changed. The two functions respectively have a free and read operations. The read operation is protected by a mutex lock, but the free operation is not protected by this lock. Thus, a concurrency user-free bug occurs. This bug had been present for over 5 years. To know more about such bugs, we studied the Linux kernel commits. We found that about 42% of driver commits fixing user-free bugs involve driver concurrency. Besides, we also studied the mentioned tools in these commits. We found that no static analysis tool is mentioned to detect concurrency user-free bugs. Thus, it is important to explore static analysis to detect such bugs in device drivers. There are some challenges to do it. The first one is how to identify driver functions that can be concurrently executed. In the Linux kernel, the documentation about driver concurrency is often poor, and there are many functions defined in the driver code. The second one is how to ensure accuracy and efficiency of code analysis. The Linux driver code base is often very large, and there are many function calls across different functions, across different source files, across different models. So in this paper, we propose our approach named DCUAF to effectively detect concurrency user-free bugs in device drivers. It performs static analysis on the LLVM bytecode of device drivers. It first uses a local global strategy to identify concurrent function pairs from driver source code. And then it uses a summary-based lockset analysis to detect concurrency user-free bugs. Let's see the local global strategy. In most cases, a Linux driver needs to implement some functions, including kernel driver interfaces and interrupt handler interfaces. And these driver interfaces are the entries of this driver. Thus, driver concurrency is often determined by concurrent execution of these driver interfaces. So we need to identify which pairs of driver interfaces can be concurrently executed. Now here are two example network drivers in the Linux kernel. The two drivers both define a global data structure whose type is struct net device ops. This data structure has some function pointer fields. Each field is a kernel driver's interface, which represents a specific driver functionality. For example, in the figure, the NDO open is used to open the device. NDO stop is used to close the device, and NDO start admit is used to transmit the packets. Besides, the two drivers both call the function request IRQ to register the interrupt handler interface. From the functionalities of these driver interfaces, NDO start admit can be concurrently executed with the interrupt handler, but in NDO open is never concurrency executed with a new clause. Based on this driver model, we use 2 stages to extract concurrent function pairs. Firstly, we analyze the source code of each driver, which forms the local stage. And then we statistically analyze the local results of all drivers, which form the global stage. In the local stage, there are 3 steps. Firstly, we identify possible concurrent function pairs in each driver. We do it by checking whether the 2 functions acquire the same lock. If so, we select the pair of them. Secondly, we draw possibly false pairs. For each pair, we collect the ancestors of the 2 functions in the call graph and drop this pair if they have a common ancestor. Thirdly, for each remaining pair, we identify the pairs of driver interfaces calling the functions and extract these pairs as local concurrent interface pairs for this driver. After the local stage, we get the local concurrent interface pairs for each driver. In the global stage, we first gather all these pairs, and then for each pair, we check how many source files have the 2 driver interfaces and how many source files consider the 2 driver interfaces as a local concurrent interface pair. We divide the 2 numbers and get a ratio. If this ratio is larger than a threshold, this local concurrent interface pair is considered as a global interface pair. And the table shows 4 examples. The ratios for the first 2 pairs are very small, so they are dropped. And the ratio for the last 2 pairs are large enough, so they are extracted. Finally, with this global concurrent interface pairs, we identify concurrent function pairs in each driver. With these function pairs, we perform a summary-based lockset analysis. It uses a context-sensitive and flow-sensitive analysis to maintain a lockset for each variable access. It performs a field-based alias analysis to identify the same locks. It performs a summary-based analysis to reuse the results of already analyzed functions. Specifically, this analysis has 2 steps. Firstly, for each concurrent function pair, it collects the lockset of each variable access in the 2 functions. And then it checks the held locksets of variable accesses to find bugs. In the evaluation, we check the driver code in Linux 3.14 and 4.19. We use a common PC with 4 CPUs and run DCUAF on 4 threads. We configure the Linux kernel using the OES config for x86. The results of the local global strategy are shown in the table. DCUAF analyzes over 5 million source code lines within 20 minutes. It extracts thousands of concurrent function pairs in the driver code. With these pairs, DCUAF finds hundreds of concurrency user-free bugs. We manually check all of these bugs and identify that many of them should be real. We also sent 130 real bugs to driver developers, and 95 of them have been confirmed. The slide gives some links to some confirmed bugs. The false positives are introduced by some reasons. For example, our alias analysis may incorrectly identify the same locks, and our flow-sensitive analysis doesn't validate past conditions. The false negatives are caused by some reasons. For example, function pointer analysis is not performed, and other kinds of synchronization are neglected. At last, we make a conclusion of our paper. Concurrency user-free bugs in device drivers are often hard to detect, we propose a statistical analysis approach named DCUAF to detect these bugs. It uses a local global strategy and a summary-based lockset analysis. This approach finds hundreds of new real bugs in Linux DOS drivers. Okay, that's all. Thank you.
All right. I have a question if no one else has a question. So you mentioned that you're using alias analysis and you're also using apparently call graph analysis, correct? Yeah. I would tend to think that you would have to use these analyses in an interprocedural fashion, like you'd have to do this over the whole Linux kernel. Is that correct, or are you actually using the alias analysis and call graph analysis only during your local phase?
In fact, the alias analysis is just performed on the driver code, not the whole kernel. And because for example, we analyze one driver, we only analyze the functions in this driver. So, for example, if the driver calls a kernel interface like maybe request IQ and keymalloc, we drop it, and we do the alias analysis by maybe renaming the names when we cross the functions.
Okay, so it sounds like you're doing interprocedural analysis within the driver, but not actually across translation units, correct?
Yeah.
Okay, so you could potentially miss aliases that would occur due to interactions between drivers or interactions between the driver and between the drivers and the core kernel, correct?
Yeah. For example, in fact, if some drivers may call the function defined in other drivers, and we may miss these situations.
Okay, but it's still good enough for finding bugs.
Yeah.
Okay. All right. Other questions? Yeah, just come to the microphone. Yeah, so if you have questions, just line up at the microphone.
Alex Kogan, Oracle Labs. So is there anything special in device drivers that make your approach work, or you could apply it to other pieces of software or the rest of the kernel?
Excuse me, can you speak louder or slowly?
Is there anything special in device drivers in the Linux kernel that makes your approach work, or you could apply it to other pieces of software or to the rest of the kernel?
So you asked whether the DCUAF can use for other software?
Yeah, basically, why did you decide to focus on device drivers?
Okay. In fact, DCUAF is can only work on Linux drivers now. And for other software, maybe our approach is based on the Linux driver model. So if we want to apply it on maybe file systems or other software, maybe we need to modify we need to know the model of this software, and modify maybe our approach.
Okay, thank you.
Hi, Spiritula Cravani, University of Rochester. So I understand you didn't do the analysis across modules, but why there was no function pointer analysis within the driver? Was that a hard step? You said that function pointer analysis was not performed.
Yeah.
But it would be only within the driver. That's what you're looking at, right?
Okay. In fact, in the same driver, maybe this driver may also cause a function pointer,
right.
But this pointer may have a function often defined in this driver.
Right.
For example, the driver calls the Ethernet controller driver calls a function pointer, and this pointer maybe have a assignment in this driver. In this driver, we cannot analyze the function pointer too.
Okay, thanks.
All right, let's thank our speaker one more time.